How's it going, and welcome back to the channel. In today's video we're going to go through a variety of BMAT Physics questions, where I'll work through the questions, telling you which equations I'm using, what sort of logic I'm using, and how we're hopefully going to get to the right answer. Now the point of these sessions isn't to get every single question correct, it's more so to show you the technique that you should use to try and get as many questions as you can correct. Thank you so much to Medify for making this video possible. Please go and check out that BMAT question bank. It's fantastic. We're going to use it in the session today to do some BMAT practice. It's amazing how they've separated out the different question types in the exam to help you appropriately revise. So let's crack open Medify and let's begin a few questions. Let's start with some physics. Which of these is not a correct combination of SI units that corresponds to energy? So AVS, or kilogram meters, so Newton's meters is force times time divided by mass. Okay, that's work done over mass. With this one, because it's not. Wow, okay, that was quite easy. I didn't even work out the others, just saw that one and tried it out, and that was the answer. Because force times time, I think, is the work done, and so that's a form of energy. So if you're dividing by mass, then that's no longer an SI unit for energy. So that was fairly easy. A bit of luck there to get it on the first one. Which of the following is not necessary in order to find the specific heat capacity of copper? To find the specific heat capacity of copper, a block of copper at 80 degrees Celsius is transferred to water at 25 degrees Celsius. You would not need to know you don't really need to know the thermal conductivity of the copper. You need to know everything else. Fair enough. Just the formula for specific heat capacity is Q equals mc delta T. So the mass of the object times the specific heat capacity times the change in temperature. That's really important. Right. 5 watt, 0.2 power source of P equals IV is connected to a shown. Calculate the power dissipated in the highlighted resistor. The power dissipated. So for power dissipated, it will be again P equals IV. We know that current is not split in a series circuit, so it'll be 0.2 amps. We need to work out the voltage of the circuit. So P equals IV, V equals P over I, which means, well, technically I don't even need to know that. Do you know why? Because I can use P equals I squared R. So I need to work out the resistance of this. So to work out the resistance of this, again, I need to work out the voltage of the circuit. So what's going to happen is we're going to have P equals IV, so V equals P over I, which is equal to 5 watts over 0.2, which is equal to 25 volts. Great. So now, RT is equal to 13 plus 20 plus 30 plus X. And then RT will equal, if I use V equals IR, R equals V over I, which is equal to 25 volts over 0.2, which is 125 ohms. That's what that's equal to. So therefore, X is equal to 125 minus 50 minus 13, which is 75 minus 13, which is equal to 62. So I've got 62 ohms there. So P equals I squared R, which is equal to I squared is 0.2, so 0.04 times 62, which is equal to 62 over 100 times 0.4, which is equal to 0.62 times 4. No, which is equal to times 4. Times 4, so that's equal to 0.62 times 4, which is equal to 0.248. But this one, my powers are wrong. Fair enough. So do you see how, let me just quickly check what happened there. So I squared R is 0.04, the resistance is 62, so I made a small mistake somewhere there, because clearly my, as you can see, my decimals were a tad off. All the answers are the same. Just trying to work out. So, was I working in megawatts? I wasn't, no. 0.62 times by 4. Because 0.04 is 4 over 100 practically. So, oh no, yes, I just multiplied. This step is wrong. Great. 2.48. Because 0.6 times 4 is 2.4. So yeah, silly mistake there. But still got the right answer. Great. When a light wave passes through one medium into a medium with higher refractive index, okay, its speed decreases according to the ratio of the refractive index of two materials. Yeah. If the refractive index of air is 1 and the refractive index of glass is 1.5, what is the speed of light in glass? Use information to calculate the speed of light. Oh, I've forgotten the formula for this. So I think it's... right, so this is where it's a prime example of where I've forgotten the formula for refractive index, which I think is N2 over N1, and that's the refractive index. So how does that affect the speed of light? So if it's 1.5, it's going to be 50% slower, which will be 2.8, I think. Great. Noise. But you see, this is the equation here. So N air over N glass is equal to V glass over V air. So this is an equation. I would therefore get a piece of paper, write down, and make sure I remember properly, because clearly I will be losing marks if I don't remember this for future use. Right, next one. So wave has frequency of 100 hertz and wavelength of 25 milliliters. So not 25 milliliters, 25 meters. So that's going to be 25 millimeters is equal to 2.5. To get into meters, I need to divide by 1,000. So it'll be 25 times 10 to the minus 3, which is equal to 2.5. And that will mean putting down is minus 2. So that's in meters. So that's C equals F lambda, which is 100 times 2.5 times 10 to the minus 2, which is equal to 2.5 meters per second. So in 14 seconds, 14 times 2.5 is equal to 28 plus 7, which was 35 meters. Cool. Okay, toy car, 4 forces. Toy motor, great. Accelerates 3 meters per second. Okay, cool. A equals that. And the toy is moving at 10 meters per second to the right. Great. So that's time would be 10 over 3, which is equal to, 3.3333 seconds. It deploys the brakes. This brings the total resistive forces to 9 newtons. So total resistive force is 9 newtons. Assume the motor is running and the drag force is independent of velocity. Calculate how long it takes the car to come to rest. Great. So, we've got a 9 Newton force. 9 newtons versus 4 newtons. So the net force is 5 newtons that way. Great. And it's traveling at 10 meters per second. So we need to work out how long it takes for it to come to rest. So F equals ma. I don't actually know the mass of the car. So it's going to be, well, does it give us a mass? It says 4 forces, to be fair. So to be fair, because the brakes and the drag force add up to 9. So I'm trying to think which equation I'd use. F equals mv over t. No, this might just be some Subat sort of question. So v equals u plus at. So the starting velocity is 10. This equals to 0 plus 0. What's the acceleration? I can't work out the acceleration. Well, to be fair, I can work out the mass, because if it's mg, if the mass is mg, then, well, like 1 is equal to mg, clearly. So let's say g is 10, then m is equal to 10, 0.1, I think. So I'm going to take mass as 0.1. 0.1 times acceleration is, I don't know acceleration. So 5 is equal to 0.1 times a, which is equal to 5 over 0.1 times a, which is equal to 50. So it's 50 times t, minus 10 equal to 50t, t is equal to minus 10 over 50, which is equal to minus 1.5, which is equal to 0.2 seconds. Because it's decelerating. Hopefully that's right. Yes! Woo! Okay, right. So DC was a bit apprehensive at the beginning there, couldn't work out the mass. Then I saw the opportunity to work out the mass using the sort of weight they give me, P and R. Well, yeah, clearly R is a downward force of weight, and weight is equal to mass times gravity. Estimate gravity to be around 10, therefore the mass is 0.1, and then F equals ma. You've got the mass now, you can work out the deceleration, and then Bob's your uncle, you get the answer. Woohoo! That's so satisfying when you get that. Right, amount of mass, 70 kilogram, is standing at sea level on a wooden deck. Great. The gravitational strength is 10 Newton per kilogram. What is the force exerted by the deck on the man? Great, 700 newtons. That's pretty easy, because, yep, Newton's laws. Electrical power is transferred in two circuits with 100% efficiency. The voltage in the first, the current. Okay, great. So P equals IV. Efficiency relates to power usually, so 10 times 5 is 50. Transfer results in 25 current. Okay, great. So the current is now 25 in the second one, so P equals IV. 50 equals P times 25 times V. Therefore, V equals 50 over 25 equals 2. Fantastic. So let's see if that's right. Woohoo, that's right. Nice. Which of the following are uses of electromagnetic waves? Ooh, electromagnetic. So, sonar I think uses sound. I think radar uses radio waves, so that must be it. Because sonar is like when you ping out a bit of sound and it goes and hits something and comes back. That's like for submarines and stuff. Radar is mostly for like, I think it sends us radio waves and like for planes and stuff, and then they bounce back. Echolocation, again, is to do with sound. You make a sound, you see how long it takes to echo and come back. Seismometer, that just doesn't relate to EM waves. That relates more to, I think, like P waves and S waves. One of them is a transverse wave, I think, but they're not EM waves. Right, next. Select a feature not found in a step-up transformer. So you do find a laminated core iron. A greater number of secondary windings than primary windings. Yes, you do, because that's a step up. Lower current output than the input current. So a step-up transformer will increase the voltage and decrease the current. Yes, you would find an output low current, right? You wouldn't find a direct, of course you wouldn't find a direct power supply, because a transformer depends on the AC current sort of changing the direction of the current, because in the secondary coil, in order to induce current, you need to have a changing, I think, EMF, which means you need to have an alternating current, which is the magnetic field that's created by the current getting in the wire, which means that magnetic field around the second coil is always changing, which allows you to therefore induce current. So for current induction, you always need AC. You can't use DC for that. Great. Okay. A 5 kilogram mass falls through a distance of 20 meters, which is attached to a 100 watt bulb. Okay. 40% of the kinetic energy produced by the mass is transferred to the propeller. Nice. For how long does the propeller keep the light bulb? Great. So this is just MGH. So that's to work out the energy initially. So it's 5 times 10 times 20, which is 200 times 5, which is 1,000 joules. Fantastic. Now, KE is equal to half mv squared. Great. So we're assuming that you're going to assume that at the end of 20 meters, all of this 1,000 joules has been converted into kinetic energy. So 40% of that is 400 joules. So then I had to put this into here. Actually, no, I didn't need to put it there. 400 joules. That's all I need. Great. So 100 watt bulb. So P equals IV, E equals ITV. Great. So it's 100 watt bulb, which means it'll be it's 100 times T. Energy is 400 times 100 equals 100 T. Therefore, T equals 4. Nice. Right. Lovely. One of the greatest dangers to passengers during motor vehicle accidents is continued motion immediately after collision. Injuries from this callous trick of Newton's first law range from whiplash to decapitation. Okay, that's pretty scary. Which of the design options below do not reduce the extent of this damage? So the point of cars is it's meant to like slow down the rate of like impact. So seat belts slow that down. The crumple zone. Brake lights definitely do not like lower that. Brake lights simply just cosmetic to alert the drivers behind you. Anti-lock brakes, yes, because anti-lock brakes, what they prevent you from doing is they prevent the wheels from skidding. So usually if you press the brakes hard and the surface is very slippery, your brakes like seize up. Whereas anti-lock, they sort of like release the brakes every so often, and that allows the car to like try and gain back some traction, and also sort of slows it down a bit more. Seatbelts sort of hold you back so they don't let you lurch forwards after the car's crashed. And same as the crumple zone is designed to, although your car is going to be written off, it's designed to sort of absorb as much of the impact by the actual car's structure to therefore reduce the impact transferred to the passengers. Noise. What are the charges in alpha and beta particles respectively? So alpha particle is 2 neutrons plus 2, so 2 protons plus neutrons. Beta particle is 1 electron, so it's -1. So it'll be +2 and -1. Lovely. Thank you very much. Last question, and then we'll call it a day. An insulator is charged by friction and gains a charge of 4.8 coulombs. Okay, how many particles are transferred to the insulator? Lovely. Right, so 4.8 divided by 1.6 times 10 to the 19 should give us 3 times 10 to the 19. So that should be the answer. Thank you so much for watching this video. Hopefully it's been very useful. You seeing me doing a few BMAT Physics questions, and hopefully I've given you a few tips whilst doing these questions to help you better perform in this section. For those of you who've forgotten a lot of your GCSE Physics and who aren't doing it A-level, this is a very hard section. These questions, these 7-8 questions that will be in the exam on physics will be quite tough. However, as you can see, they're not impossible at all. They're very feasible, and all it requires is a bit of aptitude and a rigorous approach to allow you to memorize equations and appropriately apply them when you see them in the questions. As always, thank you so much for watching. As always, thank you so much to Medify for making this video possible. Like I said earlier on, please go and check out the BMAT question bank. Use it. Come on guys, you've got just less than 2 weeks for the exam, so it's so important that you utilize the resources that are available to you and make sure you get a good mark in the BMAT. It makes life a lot easier in the application process. As always, thank you so much for watching, and I'll catch you guys soon in the next video. Cheerio.